Next session is a technical session, and then our next presenter is Pancho Dachkinov, and his topic is design and analysis of multi-material compliant joint for precision engineering application. He's from Kyushu Technology, Kyushu Institute of Technology, Japan. Pancho, over to you.
Hello. Hi, I'm Pancho Dachkinov. As Nayan mentioned, I'm from Kyushu Institute of Technology. Good afternoon and good evening to everyone. I'll share my screen. That's the topic of our work. I would like to thank you about the opportunity to present our work and also to thank the presenters so far for the great presentations. This is a collaborative work between Kyushu Institute of Technology and IIT Kanpur. That's the content of the presentation. And this is, on the left side, are models of compliant cross-spring pivots. On the right side, again, compliant joints that are 3D printed. Same models we have investigated and taken from the literature and printed them. And 3D printing of a cross-spring compliant joints performs the motion and by deformation in the elastic region, which is caused by external loading and is suitable for precision positioning and engineering application related to stabilizing mechanisms and positioning. The proposed concept is a modified of traditional cross-spring pivot, such as those shown here. And the proposed design is this one, which efficiently provides frictionless and wear-free in-plane motion. The joint's behavior is analyzed based on a nonlinear finite element analysis. And why 3D printing is very suitable for that purpose is because it is capable of printing directly assembled models by avoiding entirely the assembly process. And also we can control the infill density and therefore the stiffness from the model from the inside. And here is an example of a compliant mechanisms. Compliant mechanisms are those mechanisms that deform, that rely on deformation caused by external loading to perform the motion. This is a 4-bar mechanism. And on the right side is the same simulation of the same mechanism. So quickly, what is a very simple illustration of what is a compliant mechanism? It takes a rigidly articulated traditional joints, such as this pin joint, and they remove the articulation and replace it with a flexure that deforms and executes the motion. That leads to the several advantages mentioned here on the right side. They provide adaptive and monolithic motion, avoiding entirely the assembly process. And because there is no assembly, the joint is, there is no friction and no clearances and no generation of the heat. Cross-spring pivots are relatively simple in their design. Here is our proposal of 2 cross-spring pivots oriented of 90 degrees from each other. And here is a drawing. We can see it consists of 3 beams in one plane, and all beams have the length of L and cross-section of A, a square cross-section, and are oriented on angle alpha 60 degrees from each other. So moving forward, on the left side here you can see a 3D rendered image, and on the right side is a physical prototype. The platforms, the blue one here, are printed from a solid material called PLA, and the beams, the black one, are printed from elastic filament called TPU, and that allows for that multi-material combination allows for the platforms that attach to other components to be rigid, and the beams that execute the motion are flexible and provide a greater motion this way. The two material combination provides diversity for combining different material pairings and experimenting with them depending on the applications. However, it has to be mentioned that this is, although it's a compliant mechanism, is no longer a monolithic single unit. It is assembled. All the components have been printed separately and after that assembled. Here are the 3D printing processes in this table. In order to achieve same performance every time, we need to specify the properties and always use the same values. So for the platforms, we use PLA and TPU for the beams. They are printed on a desktop machine called Anycubic Mega S. And the slicing software is Ultimaker Cura. Here you can see the temperatures and the speeds for printing. Flexible material has some specific requirements. And on this slide, we can see on the left side are all the loading conditions in which the joint has been tested. We have compression, tension, and bending. And in the middle and on the right, we have removed the platforms and dissolved the forces for better visualization of the process. Also, for better visualization, we have marked all the beams. Here is XY plane and here is YZ plane. We have marked them with the letters and also by color. And here we can see that due to the symmetry, A and B will have similar loading performance as D and T beams. Therefore, we can only analyze A, B, and C. These are the unique combinations. And here the unit has been dissolved. We have beams A, B, and C, and we have the loads for tension, compression, and bending. You can see how they will behave if they were loaded individually. Next, moving to the results from the nonlinear finite element analysis. Figures A and B shows the results of tension and C and D of bending. As we can see on B, there is rotation of the top platform according to the bottom. This is due to the tensile forces, and there will be similar results if compression results at compression with the rotation in the opposite direction. On the right side, we can see the plots for tension and bending, and we can see the nonlinear character behave of the graphs due to the non-linearity of the material and the joint itself. And moving on to the discussion part, the proposed design of a cross-spring pivot has a geometry similar to the ligaments of the knee joint. And ligaments are tough tissue made out of collagen that is twisted like a rope and attaches bones to bones together and keeps them from sliding too far from each other. And it has stabilizing functionality for the human joints. And therefore, the application of this compliant mechanism has been inspired by the ligaments of the human knee, ACL and PCL ligaments, arterial cruciate ligament and posterior cruciate ligaments. And it can have stabilizing applications and also position for small displacements. And to optimize the stabilizing properties of the joint, 3D printing parameters such as infill density and infill geometry have to be further investigated in order to control the stiffness of the joint precisely. On this slide, we can see another example. It's the same structure, but it is printed as a monolithic single unit from a PLA. On the right side is a 3D model of it. On the left side is the 3D printed prototype. This just aims to illustrate that printing as a single unit is possible. It doesn't have much applications from PLA, but it could be very useful for printers that use with metal powder such as SOS or SOM. And then for small displacement, we will not have nonlinear character anymore, nonlinear behavior of the joint. And it will be easier to analyze. And I would like to conclude my presentation. It's the concept proposed in this presentation is a unit that consists of two cross-spring pivots that are perpendicularly oriented to each other. And it has two rotations around its center according to X and Y axis, and can be used as a compliant, as universal joint. It has similar structure, but the center of the axis are matching. The forces have been dissolved for all beams and individually analyzed depending on the various loading conditions such as compression, tension, and bending. A static nonlinear finite element method simulation has been conducted to demonstrate the nonlinear behavior of the model. Amongst the highlights of the design are its compactness. The rotational axes are matching the center points. Its compliance leads to frictionless and wear-free motion that preserves the durability and reliability of the joint in time. And the multi-material coupling can be varied, and therefore, depending from the application, many combinations could be applied of different materials. So several challenges that have to be considered in the design stage. Some experiments need to be conducted to verify the performance and to check if the buckling occurs and under what loading conditions. Also, the material failure of the joint has to be considered on the experiments. Another important optimization parameter is that not optimization parameter, but consideration is that this joint is relatively complicated for manufacturing and can only be realized by 3D printing or additive processes. And conventional technologies cannot realize it as a single unit. It has to be made as an assembly in order to be replicated by conventional technologies such as CNC machining. And I would like to thank you and welcome your questions now. That's all from me. Thanks.
Thank you, Mr. Pancho, for your nice presentation. Because of a time constraint, we can have one quick short question from the audience. Okay, I'll ask a short question.
Okay.
Can you just the physical application of your proposed model? Can you give some example of physical application?
So it can be used, several of those joints can be used together as a stabilizing mechanism for small displacements. And also it can be used as an actuator in different planes of motion as a universal joint in different perpendicular planes according to rotations according to X and Y axis. So we haven't illustrated any example because we have to further optimize the design.
Right. Thank you.
Thanks
Thank you very much
for your
for
question.
Yeah, thanks
and for the attention.
Nice response.